So I'm a materials chemist, and there are lots of cool aspects to being a materials chemist. We make new materials that may not have existed if it wasn't for us. So that's always a really good feeling to know that a material, particularly a useful material, exists because at some point we made it in a lab, or we even saw it in our dreams. But personally, for me, the most interesting aspects of being a materials chemist is when a material we make does something we completely did not expect. Even though we studied materials for many years, every now and then we have just incredible surprises along the way. So I thought today I'll tell you about a project that started off completely unexpectedly. We most certainly were not looking for white light emitting materials, but they found us. So I'd like to tell you this story that started when my group had just started, and it's a project that we're continuing on to this day. You're welcome to interrupt me along the way, but I'm going to start. I am a little slow in the morning. I don't usually wake up this early. Okay, Lahiru.
Yeah, we can see your screen well. Yes.
Okay, perfect. Okay, so this is my story for today: white light emission from layered halide perovskites. And so I told you I'm a materials chemist. My group, we synthesize all kinds of different materials, but we really have a focus and emphasis on this family of materials called halide perovskites. So let me first introduce the family of materials that we have come to love so much. So this is the structure of a typical three-dimensional halide perovskite. So a perovskite is just a name for a particular arrangement of atoms. So whenever we see this arrangement of atoms, we can call it a perovskite. So to be a perovskite, you need to have a metal at the center of an octahedron defined by 6 ligands. These ligands can be oxygen or sulfur, or it can be a halide like iodide, chloride, bromide, fluoride. And when these octahedra connect to other octahedra through exclusively shared corners, this material is a perovskite, very roughly. So we see this corner sharing connectivity and this turquoise octahedra extending in 3 dimensions. This framework that I have highlighted in turquoise has a negative charge. So to balance that charge, small cations kind of have to sit in the cavities of this framework. So when that cation is inorganic, like cesium, rubidium, sodium, this is your standard inorganic halide perovskite. But you can also imagine shoving small organic molecules into these cavities that still have a positive charge, like methyl ammonium. And in this case, this material has an inorganic component and an organic component. So these materials are called hybrid or organic-inorganic halide perovskites. The materials that I'm going to focus on today look like they have been derived from this material by taking a tiny little knife and slicing along specific planes. So I'm going to focus on dimensionally reduced perovskites. So we go from a 3D material to a 2D material, where still in 2 dimensions, you see this corner sharing connectivity. But we basically make these materials because the organic molecule we put in is too large for this 3-dimensional cavity, and therefore it separates the sheets. So both 3D and 2D perovskites have been known for many decades. And my particular favorite aspect of these materials is really how they form, because you can form really beautiful, elaborate structures that fall in the category of 2D perovskites, but they all form through this process called solution state self-assembly, which simply means you take a pot of water or organic solvent and you throw your precursors into the pot. So you can imagine there's this free-for-all tumbling mess of organic molecules and inorganic ions in solution. And our job is to find the conditions under which this crazy mess, on its own accord, chooses to form these beautiful ordered structures. where sometimes we see evidence that the organic molecules will template the 2D perovskite sheets. Other times, we've seen cases where the inorganic sheets kind of template these unusual organic architectures. So the two layers are kind of helping each other out. And the way so this is very different from the types of layer by layer deposition methods that people use to form layered materials. This is really easy once you have the recipe, once you have the conditions, which are sometimes hard to find. But once you find those conditions, you can make this over and over again. I can take a solution of this material and I can ship it to Sri Lanka. You can put it on a substrate and you'll get the same perovskite. So it's if any kind of manufacturing, this is really great because it's inexpensive and it's scalable, meaning that you can make grams of this stuff most of the time. So early on, when I had just started my group, we were kind of, exploring. We didn't quite know what we were going to do, and we were just making 2D perovskites, hoping to get a lead. And we made a two-dimensional material that basically looked and behaved the way we would expect a 2D perovskite to look and behave. So these 2D perovskites look like a slice from the 3D material, as I mentioned, and we used this organic molecule with a 3-carbon chain between the 2 ammoniums, and we formed this material. And then we asked the question, it occurred to us that these sheets were kind of pretty close to each other, maybe a little bit closer than we had seen before. And we asked, what's the consequence of removing one more carbon and making this chain just a touch shorter? So my student found out that if she were to do that, she still made a 2D perovskite, but sort of a crinkled sheet. So just like the flat sheet comes from a specific crystallographic plane where my imaginary knife is parallel to the faces of the cube in this material. If I were to angle my knife and cut along a face diagonal, I get this crinkled sheet. So we thought this was kind of neat. This particular structure wasn't new. There were other examples of other metals with this exact sheet. And we thought it would be interesting to just compare the optical properties of the two materials. So the flat sheet behaves exactly the way we expect it to behave. 2D perovskites with lead in the center and bromine in the corner. These materials are known to be blue emitters. So let me just tell you what this spectra look just in words. This material absorbs blue light and it emits blue light. So in black, I'm showing you the absorption spectrum as a function of wavelength. And you can see that there's a sharp peak at around 400 nanometers. So it's absorbing blue light. And if I shine blue light on this material, and then if I look at the emission is also blue. So it's a narrow emission, close to 400 wave numbers. This is exactly what you expect. So we thought, sometimes it's just good to get what you expect, because then you kind of know that you at least understand the materials. So we thought this was fine, but not particularly exciting. We then, just to complete, for completion, we decided to look at the optical properties of this material as well. And the absorption spectrum looks pretty much the same, but the emission was completely different. It just glowed white. And we did not expect this. We had never seen this. And to glow white, so this is called broadband white light, meaning that it has every color from 400 to 700 nanometers. It has every color of the visible spectrum. So this was extremely perplexing to us. How does one material with no obvious emissive site give us, a 400 nanometer photon, a 500 nanometer photon, 600, and so on? And it's broad, meaning that it's not discrete peaks. That there's an emission at every possible wavelength in the visible. So we've been studying the emission mechanism, which is what I'll tell you about today, but let me just take a step back and explain why we were excited. So we all know that, in life today, we don't stop work when the sun stops shining. So we spend a lot of energy for artificial illumination. So this is a picture of the globe at night, and you can see just how much energy we are using to light up our industries, our homes. I like this map because it puts Sri Lanka at the center. So we have been using many different technologies over the years for artificial illumination, and they all have some problems. So when I was going to school, we had tungsten filament lights, right? And you probably all experienced touching a tungsten filament bulb. It burns your hand. And that's because these bulbs generate more heat than light. So they're horribly inefficient. We then moved to fluorescent lights, which is more efficient. And the next step towards still more energy efficient lighting is to use solid state lighting. So solid state lighting requires the following two components. We need a UV, or more ideally a blue LED, a light emitting diode. And of course, you don't want to bathe your room in blue light. So you want to cover that blue LED with a phosphor. The job of the phosphor is to be excited by blue light. So you want to shine blue light on the phosphor, and you want the phosphor to convert that blue light to white light. Now, if you think about it, that's a tough requirement for any one material, right? How do you get excited by blue light and emit red, green, yellow, purple, orange? Most materials cannot do this. So this is the most basic white solid state lighting LED. This is the spectrum of the most basic white light emitting LED solid state lighting device that we have in the market. And the idea here is that you take a blue LED, which gives a kind of a narrow blue emission. You coat it with this particular phosphor, cerium doped YAG. And the phosphor coating is not perfect, it has holes. So some of the blue light goes through and we see the blue emission. Some of the blue light hits the phosphor and we get this very broad yellow emission. And this combined spectrum looks white to our eye. So this works quite well if you're reading black ink on a white piece of paper. But you might notice that this is not what I called broadband white light, meaning there isn't every emission from 400 to 700. Notably, there's no red. So if I don't have red coming out of my light bulb, that means there are no red photons to bounce off a red object and hit my eye, meaning that I cannot see red. So if you have ever been in a room with this most basic white solid state lighting device, you'll notice that some colors just look weird. Red looks brown, and all colors look kind of dull and muted. And of course, there are many applications where it's really important to distinguish color. And also, we want to be surrounded by, beautiful bright light with perfect color representation. So we want our light source to have every color of the rainbow. So right now, we accomplish this by mixing colors. So we'll throw in a red LED, and we'll start adding more and more components until the emission becomes white. But there are all kinds of problems with having different components in your lighting device. You can imagine that if you have 3 different phosphors, what are the chances that all 3 will degrade at the same rate? That probably won't happen. So even though you start with white light, over time, that the emission color will change. So a single material that emits broadband white light is a major target in solid state lighting research. So with respect to artificial illumination, these halide perovskites have a lot of really nice features. For one, we can change the color of the white light, which might sound a little strange, but you can imagine that if there's more red in your white light, it feels more warm. And if you have more blue in your white light, it feels colder. So we can kind of move around this area that's considered white simply by throwing a little bit of bromide or a little bit of chloride into the solution as we synthesize the perovskite. And I told you this emission is really broad. So in yellow, I'm showing you the solar spectrum at noon. And in red, I'm showing you one white light emitting perovskite. And in black, I'm showing you that same perovskite with a mixture of the halides, giving almost a perfect match to what we want for artificial illumination. So because this emission is so broad, the color rendering index is high, meaning that this red shoe looks red and it doesn't look brown. So there were lots of nice aspects with respect to applications, but what really intrigued us was, what on earth is happening? How does a material give every color of the rainbow? So first, in chemistry, whenever we encounter something really weird, something we don't understand, we blame the surface. Because all of our probes that we typically use, like X-ray diffraction to get the crystal structure, they all study the bulk of the material. You get the average structure and the average properties. We don't know how we don't know how most materials terminate. What happens at the very end of a crystal? So this is why nanoparticles show such intriguing properties, because they have so much surface. So we wondered, maybe there's something really strange at the surface of these materials. So to probe this, we looked at the emission of a really big single crystal. So in my life, a centimeter scale crystal is very big. We then took that crystal and we crushed it to a powder, and we took the emission of the powder. And the volume to surface area ratio of the single crystal and the powder are very different, right? But it turns out the emission is the same. So that told us that whatever is emitting is not restricted to the surface, it is pervasive throughout the material. So we still didn't know what was emitting, we just knew that it was distributed throughout the material. So we thought, well, the next kind of culprit that we often suspect are defects. So a defect is, some aberration in your crystal structure, some change in your structure that you cannot see through diffraction. And we thought maybe this material has all kinds of different defects, and each defect is a little bit different. So every defect will emit differently, and that's why we get this white light emission. So I'm going to use this analogy that my material is this wooden solitaire board, and when I hit this material with light, I generate electrons and holes that I'm going to use these marbles to depict the electrons and holes. So the idea is that my material has this number of defects denoted by these holes. And as I pump the material with light, I generate, let's just say, excited electrons. And when these electrons kind of fall into a hole, they emit with a lower energy because they're kind of stabilized because they're now in that hole. So if this material had a whole bunch of defects and all these holes had a different depth, I can kind of maybe persuade you that every time a marble emits, every time a trapped electron emits, it will emit a different color because each hole has a different depth. That is possible. We can test this by looking at the power dependence. So this is the excitation intensity. So how many photons am I hitting this material with? And this is the emission intensity. How many photons are coming out? And what we see is, so if we had emission from a finite number of defects, you would imagine that as you start hitting this material with photons, the photoluminescence intensity would go up, up, up. And at some point, you would saturate all your defects. And then it should show saturation effects. It should kind of tail off and then flatten. But in our cases, until we kind of burn the material, we have never seen any deviation from linearity. It's always a perfectly linear relationship. So this makes us, so with this, we can make two conclusions. Either this material has a ridiculously large number of defects such that we never saturated, which I find hard to believe in these beautiful single crystals, but it's possible. Or alternatively, this is not the correct model. We have something else going on. So what if my material wasn't, well approximated by this wooden solitaire board, which with these rigid holes? It was a much more flexible, more deformable material. And what if it was the act of generating that excited electron that created the defect. So what if my defects are in fact induced by light? That way, when I add more photons, I'm going to get more defects. So this is our current understanding of this material and white light emission from these materials. Our lattice is really soft. It's really deformable. I shouldn't be thinking of it as this wooden board. I should be thinking of this as this loosely held net. And in the ground state, at a point when this material is not being excited by light, my lattice has no defects. But every time I shine light on it, I generate electrons and holes like any semiconductor. And those electrons or holes interact so strongly with the lattice that it distorts the lattice, the same way that a soccer ball distorts a net. And the net kind of sinks into the net. So this deformation in the net is present only when the soccer ball is present. And likewise, we think that the distortion or the defect in these materials that give rise to the white light, these defects are present only in the excited state. So this phenomenon is called exciton self-trapping. So I told you I haven't been very specific about what the carriers are in this material. In a semiconductor, when you hit it with light, we generate electrons and holes. In these materials, the electrons and holes interact so strongly with each other that the excited state has excitons, and that's an electron-hole pair. So this exciton is interacting so strongly with the lattice that it is creating a defect. So this is called exciton self-trapping. So I told you that in the ground state, my lattice is perfect. And but I have to admit that no matter how much I might love my perovskites, they are not perfect. Even though we grow these beautiful single crystals that look perfect to our eye, if you look carefully enough, any material, any real material has defects. So the net that I should have shown you is not this, perfect, pristine net. It's this, this old crappy net with holes and bunched up threads. This is more appropriate for a real material. We have holes, we have vacancies, absences of atoms where atoms should reside. We have bunched up threads, interstitials, that's where an atom is found where an atom shouldn't be. We have all kinds of weird, and the surface of any material, we have no idea how any material terminates. So it's kind of a mess. This is a real material. So you can imagine if I hit the soccer ball against this net, depending on where the ball hits this net, it'll kind of it'll sink to a different depth. So self-trapping still occurs, the same way that a ball that hits this perfect net will also sink. But the native defects of this material will kind of change how much the ball sinks. So we think that these permanent defects are not the reason the material emits white light, but it kind of affects the white light by changing the emission because it changes how much an exciton is self-trapped in the lattice. So let me put all of this together in an energy scheme. You may have seen this in your classes. So this is my energy axis, and this is a nuclear coordinate. You can think of this simply as, a bond length. And I have a ground state. So this is my equilibrium bond length when no light is shining on my material. And then I have my excited state. So this is my free exciton, meaning that I have generated an electron and hole pair that doesn't affect the lattice in any way. So this would correspond to me hitting a ball against a net and the net not moving. So I have my ground state and my excited state. This material absorbs energy and goes from my ground state to the excited state. And then if nothing happens, if the net doesn't change in the excited state, I get emission back from the excited state to the ground state, and I see this blue light. This is what has been seen for many years in the field of 2D perovskites. What we encountered was a case where you still start from the ground state. you do still excite into this excited state that geometrically looks very similar to my ground state. But then in the excited state, the ball sinks. So now I have a self-trapped exciton state, an excited state that is now more stable than my ground state. You can see that the energy has gone down, but it has also shifted, meaning that the equilibrium bond distance here is very different from the equilibrium bond distance here. So maybe a bond got longer. All we know is that that excited state geometrically looks different from our ground state. So because of this stabilization, which is the difference between this minimum and this minimum, and the distortion, which is the difference between this point and this point horizontally, because of both these effects, we get a broad emission. So that's the intrinsic self-trapping. This is me hitting the soccer ball to the perfect net and the net distorting. But remember, I told you my net is not perfect. So my net could have had a hole that was always there. Now, if the ball sinks near that hole, you can see that this well looks different from this well. So now my self-trapped exciton state is a little bit different. So every time I have a ball sinking near an imperfection, I will get a slightly different self-trapped state. So we think both these mechanisms are operative. This alone explains much of the white light emission. This explains how broad the emission is and how much shifted to lower energy the emission is compared to the absorption. But this phenomenon broadens the emission still further. So for the longest time, we thought this was what was going on. We get emission, we get homogeneous emission broadening. That means emission from one state that is really distorted and stabilized with respect to the free exciton. And we get inhomogeneous broadening, meaning inhomogeneous means there's a distribution, and the distribution comes from these native defects in the material. Recently, we have lots of I didn't show you the mechanistic studies in any detail, so we did a lot of spectroscopy that led us to these conclusions. And all of our spectroscopic probes, we used all kinds of time-resolved spectroscopies, but they were on powders. We finally were able to make, big crystals, big single crystals of these materials. So we decided to study a single crystal, just to, eliminate grain boundaries and any other weird effects you might get in a powder sample. And then we got another surprise. So working with Professor Mike Phibb, who's a physical chemist, a phenomenal spectroscopist at Stanford, his group found a very strange result, which is that if he looks at the emission from this white light emitting perovskite, he found that the emission at every color, so at 400 nanometers, at 500 nanometers, and so on, had the same lifetime. So here I'm showing you an overlay of all these spectra. You just cannot see the spectra because they overlay exactly. So this is a conclusion that we did not expect. This color has the same lifetime as this color, as this color, as this color. And let me explain to you why this was so surprising. In our original model, we said we have emission from this state, from this state, from this state. And if that is true, if an exciton emits from here, or then has to move to this trap state to emit, or has to move to this trap state to emit, the blue emission has to have one lifetime, the green emission has to have a longer lifetime, and the red emission has to have a longer lifetime, because this thing has to move from one to another. They cannot all have the same lifetime, unless they are really quickly hopping from here to here to here. They're just going back and forth between these different wells. So what this one possible conclusion with respect to having the same lifetime for every color is that this exciton is very rapidly sampling every self-trapped state. which was really strange to us because, we call this a self-trapped exciton. It's supposed to be trapped, right? So what is a trapped exciton doing, going very quickly from one trap state to another? So this time scale is in the picoseconds. So that didn't feel trapped at all. So we were kind of scratching our heads wondering, how is my self-trapped exciton sampling every trap state within, it was something like, if I remember correctly, 4 picoseconds. So then we came up with another explanation. So imagine that, for lunch, I have, this big plate of, rice and curry, and I eat, way too much. And I sit on my chair saying, for the next hour, I'm not moving. I cannot move. So my potential energy as a function of time is a constant, right? I'm not moving. So I'm the trapped exciton. But imagine that the ground underneath me starts to move. It starts to go up and down, and it takes me along for the ride. So I'm not moving, I'm trapped. But because the ground kind of rises, swells, and dips underneath me, my potential energy is changing as a function of time. So we think something like this is going on, where the exciton is trapped. But what if the lattice is moving? So I won't go into the details of these measurements, but we studying many other perovskites, also with Professor Phil. We found that that is indeed true. The lattice is fluctuating, which is very strange. But there are many groups around the world now who have done studies that show that these materials are not, we see this crystal structure and we think every atom is in place. They're actually all moving at some time scale. So understanding now is that we generate excitons. They do get trapped, but then the lattice kind of moves around it, and therefore it samples different potential energies, and that gives rise to all these colors, and that also explains the fact that all of these photons have the same lifetime. So far, I've told you that the emission arises from a light-induced defect that lives for a few picoseconds in the photoexcited state. So you could wonder, what is a synthetic chemist doing about this? Because we are terrible about dealing with defects. We don't like defects because we don't know what they look like. If you gave me a structure and you told me to change one atom for another, and I know exactly where that atom is, I could think about ways to do that. But how do I deal with tuning a defect that visually I don't know what that defect looks like? And how do I deal with the fact that it's only accessible in the photoexcited state and it doesn't live for very long? It lives for a few picoseconds, well, depending on the material and the temperature. It can live up to nanoseconds, but that still doesn't give me much resolution in terms of, what does it look like? If I want to change the emission in some way, synthetically, how do I access a better material? So going back to my soccer ball analogy, I have no idea what this distortion in the net looks like. And I have no clue how to change this. But I could argue that I know what the net looks like, because that is my crystal structure. And I can argue that if I change the weave or the fabric of the net, I can change how much the ball sinks. A tighter weave, a looser weave surely should change how deformable the fabric is. And likewise, we thought it was still worthwhile to look for trends in crystal structures to see when do we get white light emission from this material. So remember, I told you that most halide perovskites give blue light, narrow blue light. Every now and then we see white light. So we would love to be able to predictably form white light emitting perovskites. at one point in my group, my students were just, making these 2D perovskites, going around with a blue laser and just shining it on all these materials, hoping that something will shine white. That was fun. But that's not something we want to do. As synthetic chemists, we want to have clear design rules so that we can access the material we want without too much random sampling. So how do we come up with a rule to say, if you had this crystal structure, you are more likely to see white light? So we decided to look at different trends in crystal structures. And my students looked at a large number of 2D halide perovskites. And they looked at all kinds of different structural parameters. I will focus on 2 different parameters they looked at, and that's the tilting between octahedra. So these octahedra these are materials with the flat perovskite sheets, which were not known to be white light emitting perovskites. If you recall, it was the zigzag sheet that gave the white light. But they looked at flat sheets, and they looked at tilting. So you can define a plane that goes through the lead atoms, and you can imagine tilting in and out of that plane, and also within the plane. So that's my this is my out of plane distortion, where the tilting is up and down. And this is my in plane distortion, where the tilting occurs within the plane of the sheet. And they found that regardless of how much in plane tilting there is, if there is no out of plane tilting, the emission is always narrow. This is the emission that people have been seeing for many years. But even in perovskites with flat sheets, if there is substantial out of plane tilting, you get more and more of this broad emission along with this narrow emission. And there's this equilibrium between the two. So what is perhaps more compelling is to say that my students looked at 50 different parameters and found no correlation between any of those parameters and this white light emission. So this is the ratio of the broad emission to the narrow emission, except for this out of plane tilt. So this is still in the ground state. This is still the average crystal structure. So this is not the emissive defect, but we like to think of this as a distortion that kind of primes the material so that it can do whatever it needs to do in the excited state in order to get the white light. And since we published this paper, every time we come up with a white light emitting perovskite, we throw that data point here. And my friends tell me that they've made white light emitting perovskites, and they check whether it fits this line. And so far, the data are falling on this line, meaning that there is some correlation here. The correlation is getting stronger. I say correlation because it's just an empirical observation that this out of plane tilt is helping. The more out of plane tilt you have, the more of the broad emission we get. So we are moving closer towards a design rule for predictably making these materials. So with that, I think I should end. I have a phenomenal group of students who have done all this work, and I'm funded by these agencies. I want to leave plenty of time for questions. So let me stop here. Thank you for listening. I'm happy to take questions.
Thank you very much, Professor Hema. Indeed, it was a very interesting presentation, and you have explained it in a very, very fascinating way as well. Like you said, I hope you have a few minutes for questions. So now it's time for the discussion. So if there are any questions, please feel free to ask the questions from Professor Hema. You may take the raise hand option, or instead you may take the chat option to type in your questions as well. So now it's time for questions. So let's proceed. So if there are any questions from the audience, please feel free to raise the questions. Professor Hema, I have a few questions, if I may. So you spoke about the driver self-assembly process, which leads to these beautiful, beautiful crystals. So what exactly is the driving force for the self-assembly process?
Yeah. So I think it's safe to say that, entropy is against us, right? Because you're going from this disordered mess to this beautiful ordered. So enthalpy has to overcome it. So there are lots of hydrogen bonding interactions. So in all of the organic molecules, let me just show you. So all of the organic molecules in this material so far are primary ammoniums. So there's a lot of hydrogen bonding between these ammonium hydrogens and the terminal halide as well as the bridging halide. So that matters quite a bit. These interactions also matter quite a bit. So these are all non-covalent interactions, and there are so many of them that I think they overcome the disordered state.
So these perovskites has to be pretty thermodynamically stable, I guess.
One more time.
And so these perovskites probably are very stable thermodynamically?
They're not that stable. It depends on the composition.
Okay.
It depends a lot. So for example, this 3D perovskite, right? This material has created a lot of excitement in the field because this has some really nice photovoltaic properties. But it also has methyl ammonium, which is, methyl ammonium and iodide can, if you heat this, at 60 degrees, you lose methylamine. Mm-hmm. So they're not heat stable. Some of these materials are not light stable. Some of them are not. So this material is not moisture stable. Mm-hmm. So in another research effort in my group, we showed that 2D perovskites can make solar cell absorbers, which were much more moisture stable, simply because this larger organic molecule is more hydrophobic. So they're not super stable. They're not as stable as the oxides, which you can, heat in a furnace at 1500 degrees. So things that form in solution also come apart more easily. But it depends on the application. You can encapsulate this material, and even the white light emitting materials, like we put it on a LED and we excited it for a month under inert atmosphere. It was fine.
Thank you for the answer, Professor Hema. And my next question is actually about the process that happens in an LED light bulb. As you explained, we initially use a blue light, if I'm not mistaken, right? So why do we rely on a blue light? Can't we use any other color for that matter?
So I think what's easiest is down conversion. So you had to excite with energy higher than you need, and then get the emission at lower energy. It's very hard to get emission at higher energy than excitation. That requires like multiple processes. Up conversion is very difficult and inefficient. So you could use UV light and then down convert to visible, but people don't want to use UV light because you don't want UV in your house.
Yeah.
Because if your phosphor isn't perfect, you're going to get bathed with UV light. Probably not a good idea.
So blue is the alternative.
So out of the visible, blue is the highest energy. So I think you hit with blue and then you down convert to all the way to red.
Okay, that makes sense. Thank you very much, Professor Hema. And one more another point that was very interesting to me was about when you spoke about the disordered structures and all the defects in your structures. So to me, it sounded like partly what's responsible for this phenomena are the defects that's present on your crystals, if I'm not mistaken. So in that sense, Professor Hema, what do you think you would observe if we, instead of using these very nice single crystals, if we had used amorphous materials, will we observe the same kind of effect?
Yeah, so we asked the same question, and we tried to kill the emission. So we found a composition that was a white light emitting perovskite, and we could do a very slow crystallization. So when you slow down the crystallization, the precursors have a chance to kind of come together, fall apart, come together, fall apart, and that corrects any defects you form in the crystal. And you can make really nice big crystals. And then we took that same composition and we crashed out the crystals, as fast as we could, so that without allowing for any kind of correction. So usually you get much more defects when you crystallize something quickly. We took these materials and we pulverized it in a ball mill, just beating it up. We did everything we could to mess with the defects, and it didn't change the emission in any way. So we concluded that if it's a defect, it's remarkably stable, or it's not a defect. So that's why it's all these smaller experiments that led us to the conclusion that what's emitting is not the defect. Even if we had a perfect crystal, we would still get white light from it. That's what I think. Because of the self-trapping phenomenon, even in a perfect net, the soccer ball will still sink. But having defects further broadens the emission. Because remember, I also told you that lattice fluctuations are occurring. So even in the perfect net, the lattice fluctuations are still occurring.
Exactly. Interesting.
There's a lot going on.
That was partly my next question, actually, because I was going to ask what would happen if we do not allow perfect self-assembly to take place. Like, I mean, if we use some means to disrupt the self-assembly, what would we expect, right? I mean, that's exactly what you have tried out, if I'm not mistaken.
Yeah. There's a large temperature dependence to the emission as well. So, for example, if we cool it, the emission gets much brighter, but the width gets narrower.
Okay.
So that also tells us that these, things are moving. There are these phonons, vibrations. All of these are leading to the emission broadening.
Okay.
Yeah, the only way we can kill the emission is if we start throwing in impurities. And there are certain impurities where the excitations kind of funnel to that impurity and it quenches the emission. But if we don't change the composition, we haven't been able to change the emission through crystallization methods.
Very interesting. Thank you very much for your answer, Professor Hema.
Yeah, sure.
Are there any other questions from the audience?
And call me Hema.
So everyone in the audience, please feel free to raise your questions. I mean, this is the perfect way to engage and find out the answers to your questions then. So therefore, please feel free to raise your questions. Like I said, you may take the raise hand option, or you may even unmute yourself and raise the questions. Or else instead you can.
Yeah, thank you, Lahiru. I think I must thank Hema for making this wonderful presentation. And I think it's timely. We are going through all these energy issues, and I can see some light at the end of the tunnel, like, we are getting white light. So Hema, how hard are they to make these compounds? I was a synthetic chemist, so I'm very much interested in so I saw some literature, they were very old, so you have actually given new life to some old family of compounds. So how hard are they to make those compounds?
Yeah, so once you have the recipe, like, the concentrations, the solution, the temperature, things like that, it's really quite easy. It literally is take a pot of water, throw, lead bromide and the organic, the bromide salt of the organic ammonium, and you just allow it to crystallize. And even the crystallization is pretty simple. It's, let the solvent evaporate or let another solvent diffuse in. So it's really simple once you figure out the conditions. Sometimes it takes quite a bit of work to figure out the conditions. So, I realized I was going around telling everyone how easy these things were to make, and then my students were complaining, saying, it's not that easy. But yeah, once there is a published prep, it's that's kind of the beauty of self-assembly. And you can also even deposit films.
Yes.
You just take the precursor solution, you just drop it onto a substrate, and then when the solvent evaporates, you form a film. And what's really nice is with these layered materials, the layers are parallel to the substrate.
Okay.
Yeah, so you're right. These materials were around for a long time, which is why we were really hesitant for a while. We were wondering, why didn't anyone else notice this was white? And what was up? Like, why is it always blue in the literature, and why do we have white? So for about a year, we were like really nervous about, did we do something wrong? Was there an impurity in the lead? So I was worried that there was an impurity in the lead. So one of my students finally went to another university, used their lead, and made the white light emitting material. And at that point, I thought, okay, it's probably not the lead. And by this time, this field has exploded. There are groups around the world making white light emitting perovskites. So I don't think it's an impurity.
Okay.
Oh, it's an impurity that's in every lead source.
Thank you very much, Hema.
Yeah.
Thank you, Madam Siti. Are there any other questions from the audience?
I see something in the chat from Mikaya De Silva. Wants to know why I was inspired to be a chemist. Yeah, so when I came to the US, I had no idea what I wanted to do. I just knew that I did not want to go to med school, which is, so I got into med school in Sri Lanka, and then at the last minute, I decided I don't want to do this. So I came to the US thinking I want to study science, and I thought I wanted to study molecular biology when I came to the US. And then it's funny, I decided I wanted to major in molecular biology before taking any courses in molecular biology, which in retrospect was a mistake. But then once I took biology courses, I realized, it's not doing it for me. And then I kind of liked chemistry, but I never really loved it when I was taking the courses. It was, something I could do. And because, in Sri Lanka, the syllabus, the curriculum is actually really strong. So by the time you study for your A-levels and you're studying to go to med school, the chemistry that you learn is basically, the first 2 years of US college. So I came to the US and I realized I already knew all this stuff. So it was a great head start for me. And the only problem is they teach in English. So you have to kind of switch. I studied in Sinhala. So I basically had to learn translations while everyone else was learning chemistry, which was kind of interesting. So I liked chemistry, but the reason I decided to become a chemist was not because of any course I took. It's because of as a part of the undergraduate curriculum, you had to do research. So I kind of figured I want to be a chemistry major. It was kind of a half-hearted decision. I basically couldn't figure out what else to major in. But then once I decided to be a chemistry major, I shopped around for labs. And then I met this professor in solid state chemistry who was, super excited about his work. And I just enjoyed talking to him. So I decided to join his lab, even though I didn't really understand what he did. So I joined the lab, and then I realized, this is what I want to do. Like, it was very different from any course I had taken. Courses have a lab component, but I didn't even like the lab components that much. It was fine. Everything was like, it's not that I disliked anything, but what really inspired me to be a chemist is, the independent research I did as an undergraduate, where I made materials, and, my professor would say, do you realize that you are the first person on the planet to see this material? And I would think, oh, wow, that's pretty awesome. So that feeling that, a material exists because of me, I'm the first person to see this. I saw this material kind of in my dreams before I even made it. Just to see that first glimpse, that's what does it for me. Even now, now I don't do anything. I just sit in my office and my students tell me what they're doing. But, maybe I'm not the first person to see it, but maybe I'm the second. So that's why I'm a chemist, because I love seeing the new materials at the point of discovery.
Thank you, Hema. That was a very nice answer, because as you know, there is a rat race to do medicine in this country.
Oh, I know.
I was wondering how we could inspire the young generation to do science, mathematics, chemistry, physics, and things like that. So maybe at a later stage, I must get you to talk to our younger people, people who are like uncertain about what to do next, that is later. Not now. Thank you very much.
Oh yeah, happy to talk to anyone who wants.
Yeah, definitely. And thank you, Hema, because I mean, that was perfectly what we wanted to hear from you, because the overall objective of this webinar series is to actually inspire the next generation, because we believe that Sri Lankan undergraduates have a lot of potential in them. So they actually,
Oh yeah.
if we just give them the impetus to achieve high heights, so they will definitely go there. So therefore, seeing people like you and hearing to what you have achieved in life, I mean, that's exactly what we want our younger generations to see and get inspired. So therefore, thank you very much for being here with us. I mean, I'm sure you have much more things to do today, because we are just starting the day, although we are almost at the end of our day. So, I mean, it's definitely a very busy and very tight schedule. So thank you very much for being here, Hema. And I mean, before we let you go, I have one last question for you, Hema. That is, I mean, what is the overall message that you have for our younger generation? Because we have a lot of people entering university each year, and just like you said, there are a few people who actually drop joining the medical faculties or perhaps even the engineering faculties, and they join science faculties instead. Even when I was in college, there were a few people like that who had dropped, they decided not to go to medical college, they decided not to go to engineering, instead they join science because purely for the interest of learning the subject, and they have been doing remarkably well as well. So I mean, many people in this audience today are actually at the turning point of their life where they are trying to decide what they exactly want to do with their life. I'm sure most of the people are actually following a bachelor's degree or science degree. However, they are trying to decide whether they want to go into industry, whether they want to just stop learning altogether, or whether they really want to go into higher studies. So to all those people in the audience, what is the one last piece of advice that you would like to give him? As a Sri Lankan, I would say.
Well, I just want to point out, it's not just me. Like anytime I talk to my colleagues in the US and, they find out I'm from Sri Lanka, they immediately say, oh, I had a phenomenal student from Sri Lanka. Like I think Sri Lankan students in the US have a very good reputation as being, very hardworking. They come with a very strong preparation. Like this is just uniform throughout my interactions. Like no one says I had a student, yeah, period. They say I had a student, and then they talk for the next 15 minutes about how wonderful that student was. So I think Sri Lankan students are the preparation you get in school is really good. Like, as I mentioned, the first 2 years of college in the US is kind of similar to the chemistry and physics you learn. So it's definitely in a strong position to do higher education in Sri Lanka or abroad, and you can always come back to Sri Lanka, armed with that. I don't know if I have any great words of advice, but for me, I wasn't thinking. As you said, everyone says, if you're at this point, if you're at the top of the list in school, then you have to go to med school. So I wasn't thinking. I said, oh, I probably have to go to med school. And then it was at the last minute I realized I really don't want to do this. So I think it's great that students are kind of really asking, what do you want to do? And it is like there are practical applications. I mean, you do want to pursue something where you will get a job. But if you are interested in chemistry, then there are so many ways you can go. It's a very useful degree to have. So for any strong students in Sri Lanka who want to go abroad, learn further, and then come back to Sri Lanka, I think these students do really well. The one thing I'll say is that I'm in the admissions board. I'm in the admissions, what do you call this, committee for graduate admissions. And there's a huge weight on research. And that's where sometimes I think it's not fair for international students, because some international students don't have the same research opportunities as students in Sri Lanka. So if in Sri Lanka you can provide research opportunities for your undergrads, because everything else looks great. I mean, the grades are great, the letters are great. The only thing that's lacking is, research experience, which I completely understand, but you just don't have the same ability to do research, especially as an undergraduate. But if you can somehow give that option, if a student can, write a paper, any paper, just to show that the student knows what research is about and how to write a paper, I think that would really help any student who's trying to apply. Or even if you have no intention of going abroad. I think once you build a critical mass and you start like collaborations, international collaborations and stuff, just getting a paper as an undergrad, I think is a huge boost for anyone, because you finally realize, oh, I can actually do this.
Yes, Hema, I think you have raised a very valid point. I mean, for most of the Sri Lanka students in Sri Lanka, if a person is specializing in chemistry or any other scientific subject, the research component is compulsory. So they will definitely be engaging in in some research. However, like you said, there are many limitations in terms of the resources, the chemicals, and obviously the instruments as well. We do have a lot of limitations. So, but there's another group of students for which the research component is actually optional. And unfortunate thing is, most of the times when it becomes optional, the students just decide to opt out of the research, thinking that it would consume a lot of time and it will be difficult than just following a theoretical course. So they just decide to opt out, which is something that we are trying to change. Because I mean, even though the research component might be optional, it will definitely add a lot of value to their degree, just like you mentioned. Therefore, I mean, as educators, we are also trying our best to and make them understand the beauty as well as the importance of research. So once again, that's why we are all here today. So I'm sure after listening to you, maybe we would have a few heads turning around and coming back to do research with us. So hopefully, I mean, that's definitely the message going across. So therefore, thank you very much for pointing out that out, because that I believe is something that's very important for all our undergraduates to hear. And like you said, I mean, if there's a possibility for research to be published, that once again will be another level of qualification. So therefore, publications is something that we really need to work on, because I mean, we don't have that culture of aiming for a paper, because most of the time people think research is all about doing experiments and putting it into a book thesis. That's it.
Yeah.
I mean, there's definitely much more things beyond that point for research, because I mean, it's all about translating the knowledge to the future generations, which is what we do through publications. So once again, that's a very valid point. So I think as academics, that's something that we need to inculcate in our students. We need to promote more and more publications, and definitely that will take them a long way through. So thank you very much for that beautiful advice, Hema. I think that's exactly what we wanted to share to this beautiful audience. So thank you very much. So we have taken a lot of your time. So thank you once again for joining us. So before further ado, now I would like to invite Dr. Dinusha Udukwala, who actually coordinated this entire event, to propose the vote of thanks. Over to you, Dr. Dinusha.
Thank you, Lahiru. On behalf of the Section E2 of Sri Lanka Association for the Advancement of Science, it's my privilege to propose a vote of thanks to those who have contributed to the success of this third webinar on the webinar series of Sri Lankan Chemists in Focus. At the outset, I would like to express my sincere gratitude to our resource person, Professor Hema Karunadasa, Associate Professor of Chemistry and Senior Fellow at the Precourt Institute for Energy, Stanford University, USA, for sparing her invaluable time to grace the occasion despite her busy schedule and enlightening us with her knowledge. Thank you very much, Professor Karunadasa. I'm very sure that the audience were very much interested on the information delivered on white light emission from layered halide perovskites. Then I would like to express my earnest appreciation to the General President and the Council of SLAS for allowing us to conduct this webinar. Also, I would like to extend my thanks to the members of SLAS E2 committee especially the organizing committee for the continuous support they have given to organize such a valuable and informative session. At last but not the least, would like to thank everyone who participated for this webinar, and we hope to see you in the near future with another webinar under the webinar series, Sri Lankan Chemists in Focus. Thank you. Have a pleasant evening. Over to you, Lahiru.
Thank you very much, Dr. Dinusha. So before we wrap things up today, because our interactions were limited to this online platform, I would like to invite all of you gathered here today to turn on your cameras if possible, because we would like to capture a screenshot, because that is the least that we could do. So therefore, please turn on your cameras and we will save. We'll capture a screenshot as a souvenir of the event today.
It's great to see so many people.
I mean, it's definitely a tough time here in Sri Lanka, as you know, Hema. And
I do.
We didn't expect so many people to turn up because I mean, we have power outages throughout the day, so people have a lot of difficulties in attending even online things, online activities.
Yeah,
so we were
it's
really
impressive that you're all here. Yeah.
But we wanted to keep the momentum going on, because I mean, people want some distraction of all the things happening around us. So we thought of continuing with the activities, and with your permission, we wanted to have this activity as planned. So thank you once again for agreeing to be here.
Oh, of course. Yeah, as I said, it's really impressive that you keep going under these crazy circumstances. And I hope it's only for a very short while.
Yes, we hope so too. So I've captured some screenshots. So thank you very much for turning on your videos. So okay, Professor Teshini just turned on the camera now. So let me capture another screenshot.
Hi, Hema. Good to see you. I'm so sorry. I had this other, workshop. So I got late to join. I entered this in my calendar, but, it was kind of, we organizing a lay abstract writing workshop. So we were having a chat with Nalaka Gunawardana and Dr. Jayanta Vatavidana. So I'm so sorry I missed it.
Oh,
anyway,
I think it's
I'm sure it was wonderful as usual.
Good to see you, Teshini.
Yeah, good to see you.
And you didn't miss anything.
Another product of Ladies College, am I right?
Absolutely, we were cops together.
Okay, so thank you very much everyone for turning on your cameras, because I mean, we would have loved to have this event in person, but unfortunately due to the social situation, we are stuck with this online platform. In a way, I think it's good, because now we have the capacity to encourage people to join in at unusual times, and also we have the privilege to get people like Hema on board in providing their insights to events of this nature. So therefore, I think we have to look at the bright side of having these online events as well. So thank you very much once again, Hema, for joining us. It was indeed a privilege to have you here today. And also, last but not the least, I think everyone who had gathered here today deserves credit, because I mean, everyone is going through a lot of difficulties. So amidst all those difficulties, thank you very much for taking your valuable time to join us this evening. So with that, we have come to the end of the event today. And just like Dr. Dinusha informed, we do have a lineup of events. So therefore, please stay tuned, and we will definitely be looking forward to have you join us with our future events. So thank you very much. Have a very pleasant evening, and have a very nice day, Hema. Thank you.
Thanks, everyone, and good luck to all the future chemists.